going to go through some of the Chapter 8 test review solutions. Okay, starting with 1, 2, and 3. And if you look at the handout that I gave you in class, 1, 2, and 3 come from 8.2. So if you're looking at your notes, these come from 8.2. Okay, so first thing, if we look at number 1, okay, we'll start with identifying the transformations. So there's an x plus 2 down with the x says this is going to go to the left 2. And the minus 3 out by itself is going to tell us that this function is going to go down 3. At 8.2, we talked about reciprocal functions, which had the two asymptotes at the x and y axis. So if we take those two and we shift them left 2 and down 3, we have a new asymptote at -2. And then down 3, so we've got a new horizontal asymptote at +3. Or sorry, at -3. Okay, so that's the first thing that I'm looking for. And the two asymptotes. If you get the asymptotes, that kind of helps you with the domain and the range. So the domain is all x values, except for we said x cannot be, since we went left 2, -2. So here's my domain. Okay, the range is normally y can't be 0, but since we shifted it down, it's all y values that cannot equal -3. Okay, so we've got domain, we've got range. So the last thing we've got to do is we've got to get the rest of the graph. So I told y'all for these reciprocal functions to remember 2 points. And the first point is 1, 1. And the second point was -1, -1. So from these new axes, I'm going to go up 1, over 1, put a dot. And then I'm going to let the asymptotes kind of guide where I go from there. On the other one, we're going to go left 1, down 1. And again, from there, we're going to let the asymptotes kind of guide the shape of the function. Okay, so there's number 1. Number 2, we're going to do, okay, the same way. This time, there's nothing with the x, so it doesn't move left to right. The +5 on the outside does tell me that it's going to go at 5. The negative here tells me it's going to reflect. And since we're multiplying by 2, which is a number bigger than 1, it is also going to stretch my function. Right, so this is for number 2. With that, we can do domain. If it doesn't move left or right, then the x value cannot be 0. Okay, for the range, since it moved up, y cannot equal 5. So we're going to start with my asymptotes. Maybe this will work better if I try to draw this way. Okay, so again, doesn't move left to right, so I have a vertical asymptote at 0. And since we said it went up 5, the new horizontal asymptote is going to be at 5. Hey, we said again, we're going to scale what we call the 1, 1 point. So usually the graph has the point 1, 1. And the second point I told you to remember was -1, -1. But for this function, we are scaling it. We're multiplying by -2. Anytime you have a reflection or a stretch, you're going to scale the y value of the 1, 1 point. So I'm going to take this and I'm going to multiply by -2. And I'm going to multiply this y value by -2. So I get 2 new points. The first one is 1, -2. And the second one is -1, +2. And these are the points that we're going to use, but again, we're going to use them centered around my new x and y axis. So I'm going to come right 1, down 2, put a dot, and then I can use my asymptotes to kind of guide where I go from there. And the other point is -1 up 2. And again, I'm going to use my asymptote. So this time we had a stretch, a reflection, it went up and did not go left or right. Okay, so with that, we're going to do one more. Okay, here's number 3. This time there's a ×3, so it is going to stretch. However, since there's not a negative sign, it's not going to reflect. The -6 down with the X says that it's going to go to the right 6. And the -2 to the outside says that it's going to go down 2. So I'm going to start by drawing my asymptotes. Again, this time we're going to go to the right 6. Well, it's not quite where I want to. Let's try this again. Okay, so I'm going to go to the right 6. There's my first asymptote. And it also says it's going to go down 2. So I'm going to go down 2. Okay, so here are my 2 asymptotes. And that accounts for the right 6 down 2. This time we're also going to stretch. So similar to the last problem, we're going to scale the 1, 1 point. So I have 1, 1, and -1, -1. So this time, we're going to multiply the 1 and the -1 by 3. So we're going to multiply by 3. So the new points that I'm going to use are 1, 3, and -1, -3. But again, we're going to use them like the asymptotes created a new origin or a new x and y axis. So from here, I'm going to go over 1, up 3. And then I'm going to let the asymptotes kind of guide the shape. And I'm going to go to the left one, down 3. And again, let the asymptotes kind of guide where we go from there. Okay, so there's the first 3. Again, they come from 8.2. Those are my reciprocal functions. Oh, I forgot domain and range, so let's go ahead and add that real quickly. If we have left, right, up, or down, domain always goes with h, so it's x cannot equal 6. And the range always goes with k, so the y cannot equal -2. All right, so the next couple, we did one like this in our notes where I gave you the graph, so it's the same type of thing. I'm giving you the 2 asymptotes, and I'm giving you the parent function, y equals 4 over x. So the x equals is like the h, and the y equals is like the k. So all I really want you to do is write this as a new function. So I have y equals 4. The h goes down here with the x, but since it's just 0, there's no change, so I'm just going to put x. The k always comes to the outside, and k does what it says. So if we want this to move to y equals 4 up 4, I'm going to put a +4, and I am done with that one. Okay, number 5, similarly, the x is like the h, and the y is like the k. So we're going to start again with the parent function, which is 4 over x. And this time we say we're moving it to the left 2, so I'm going to come put 2. Okay, the trick with the h is we always use the opposite. So here where we have a -2, we're going to put a +2. Okay, the k is the good k, does what it says, and since it says -3, we can go ahead and put the -3. So we are done with 4 and 5. Okay, 6 and 7 are probably the 2 longer questions. We ask for a lot of things. So let's first ask for domain, Okay, points of discontinuity. We need x-intercept, y-intercept of each rational function. We're then going to determine if each discontinuity is removable or non-removable. So I'm going to start with number 6. First step that you should always do for these problems, if it's not done for you, is factor. So I'm going to write in factor form. In the top, there's a 3x minus 3, so I can factor out a 3, and I'm left with x minus 1. In the bottom, we have difference of two squares, so square root of x is x. So I have an x plus something and an x minus something. And then the square root of 1 is 1, so I've got x plus 1, x minus 1. A second thing we do is find our points of discontinuity. Our points of discontinuity always come from the denominator. Okay, so the denominator of the x plus 1 says we have discontinuity at -1. And the x minus 1 says we have discontinuity at x equals 1. Okay, we're then going to see if we can cancel any of these pieces. So if you notice, we've got an x minus 1 here in top and bottom. So we can rewrite this as 3 over x plus 1. Okay, if it cancels, we call this removable discontinuity. So here at 1, which came from the x minus 1, we have removable discontinuity. And removable discontinuity, if you were asked to graph it, would create a hole at the graph. Here the x plus 1 does not cancel, so the x minus 1 is non-removable, again, because it always goes with the opposite. A non-removable discontinuity would create a vertical asymptote if we were to graph it. Okay, so the last couple things here, the x and y-intercepts. To find the x-intercept, we said we're going to let y equal 0, or the shortcut was to set the numerator equal to 0. Now, the only thing with x and y-intercepts that I need to remind you is that you're always going to use the reduced fraction. Okay, so when I talk about the reduced fraction, that is this right here. So when it comes to the x and y-intercepts, this is the piece that we have got to use. So if I come and set the numerator equal to 0, well, that makes 0 equal to 3. Since there are no more x's in the numerator and 0 does not equal to 3, then we say that there is no x-intercept. Okay, last piece here, 4. We can then find the y-intercept, which is similar, but the y-intercept we let x equal 0, also using factored form. So to find the y-intercept, we have 3 divided by 0 plus 1. Well, 0 plus 1 is just 1, and 3 divided by 1 is just 3. So the y-intercept is 3, or if you wrote it as a point, would be the point 0, 3. Okay, I'll take either one of those. And that gives you everything that you need for question 6. And so 7 is the same thing, but this time step 1 is done for you. I've already factored. So we can go ahead and write the discontinuities. So we have discontinuity where the denominator is. So the x minus 2 says we have discontinuity at x equals 2. And the x minus 3 says we have discontinuity at x equals 3. We're then going to see if anything cancels. So if we look at this, again, we have an x minus 2 in top and bottom. So I can rewrite this as a -3 over x minus 3. And the discontinuity that cancels, or the 2, is called removable. And if you were to graph this, there would be a hole there. The x equals 3, since it does not cancel, is called non-removable. And since it does not cancel, we have a vertical asymptote there. Okay, so we have points of discontinuity. With points of discontinuity, it's also the same as domain. So if you get points of discontinuity, you also have the domain. So domain is all values or all real numbers except for x cannot equal 2, x cannot equal 3. So it's all real numbers except for 2 and 3, because those are where we have discontinuity. So we now have domain. The last couple things we need are the x and y intercepts. So again, x-intercept, you let y equals 0, or if it's still a fraction, the numerator equals 0. And again, we use the factored form. So similar to the last one, if we plug this in, we get 0 equals -3. Since there are no more variables in the numerator, that means that there is no x-intercept. Okay, but sometimes you will, and I'll show you another one later in the review that does have an x-intercept, so y'all can see what it would look like if you do have one. I think 14 has an x-intercept. Okay, if I then find the y-intercept by setting x equal to 0, again, using factored form, I get -3 over 0 minus 3, which becomes -3 over -3, which is just 1. So you can tell me that the y-intercept is 1, or as an ordered pair, it's the point 0, 1. Okay, the next couple problems ask you to find the vertical asymptotes and the holes for each of the irrational functions. So similar to what we were doing before, but we just have to look at discontinuity and then talk about what kind. So kind of again, a reminder, discontinuity comes from the denominator. It comes from the denominator. So if I look here, the x plus 6 says that we have discontinuity at x equals -6. So then you've got to ask, okay, does this x plus 6 cancel with the 5? If it does not cancel, then we have a vertical asymptote. We have a vertical asymptote at x equals -6. Okay, number 9, same thing. We look at the bottom and we say, okay, that tells us where things are happening. So we have something happening at the opposite of -2, so 2. And we have something happening at the x plus 1, so x equals -1. If I then come and look and see what cancels, the x minus 2's can cancel. If it cancels, then we have a hole. So at 2, we have a hole in the graph. If it doesn't cancel, so the x plus 1, then we have a vertical asymptote. So we have a vertical asymptote at -1, we have a hole at x equals 2. For 10, same thing, but this time we have to factor. So I'm going to start by factoring the numerator. Factors of 16 that subtract to give me 6. Well, that's 8 times 2. 8 times 2 gives me 16. 8 minus 2 gives me 6. But since it's a -6 here, the bigger of these two numbers has to be negative. Again, when it comes to the discontinuity, the asymptotes and holes, all I care about is the denominator. So we have something happening at x equals -2. Then we just have to determine if it cancels. If you look here, the x plus 2's can cancel, which makes x equal -2 a hole in the graph. Okay, the next few ask for the horizontal asymptotes. So again, if you're looking at your notes, this was a part of 8.3, I believe. There are 3 cases. Okay, there are 3 cases that we did for horizontal asymptotes. No matter which case we use, we said we're always going to compare the lead term. So for the first one, number 11, you're going to pretend that this is y equals 3x over 4x. And you're going to reduce. The x's cancel and you get 3/4. If all your x's cancel, then we have a horizontal asymptote at y equals whatever number you're left with. So in this case, y equals 3/4. Okay, if you look at 12, same thing. This time I have a 5 and an x. So for 12, I end up with a 5 over x. And in your notes, we said anytime we have a number over x, x in the bottom means we have asymptotes. And we said anytime it's a number over x and not all the x's cancel, we're going to have a horizontal asymptote at the x-axis. Okay, the x-axis is the line y equals 0. Okay, so here was case 2. Okay, case 3, again, I have my lead term, so I have my 2x to the third and my 2x. So if I look at this as 2x to the third over 2x, 2's cancel, one of the cancels, and I'm left with x to the second. Notice how this time there are no more x's in the bottom. If you end up with no more x's in the denominator, then that means that there's going to be no horizontal asymptote, and that is my case 3. All right, so 14, we're going to sketch the graph of each rational function. There are about 4 or 5 different things we're going to look at. The first thing we're going to look at is the discontinuity. Okay, so again, discontinuity comes from the denominator here. So the x minus 2 says we have discontinuity at x equals 2. And the x plus 3 says we have discontinuity at x equals negative 3. Since neither of these pieces cancel, we're going to have 2 vertical asymptotes, okay, one at each of these values. So I'm going to draw a vertical asymptote at 2 and a vertical asymptote at negative 3. Okay. The second thing we're going to look at is if there are any horizontal asymptotes. So horizontal asymptotes, it's a little bit tricky because we need the lead term. Well, the top is easy. We have an x. On bottom, if you multiply x times x, we get x to the second. And that's going to give you a 1 over x. Anytime we said we have a number over x, we're going to have a horizontal asymptote at y equals 0. So I'm now going to graph a horizontal asymptote at y equals 0, or the x-axis. Okay, from there, we usually look at the x and y intercepts. So again, to find the x-intercept, you let y equal 0, or the numerator equal to 0. And this time we have it, so I'm going to let 0 equal x plus 6. Subtract 6 from both sides, and I get x is equal to negative 6. This doesn't happen a lot, but it is possible to have an asymptote and an intercept. Okay, so I'm going to go ahead and put my dot there. The fourth thing that I'm going to do is look for the y-intercept, which you get by letting x equal 0. So if I come up to my function, I end up with 0 plus 6 over 0 minus 2 times 0 plus 3. That 6 over ends up being negative 2 times 3. And 6 over negative 6 is just negative 1. So I'm going to come to negative 1, put it up. So if you have a point that kind of helps you get started, then you can use it. So this piece right here is bound by these three asymptotes. So it may not be perfect, but if we were sketching, we know it's got to come here and here. Okay, what we don't know is what's happening kind of on either side. So what I want to do, okay, so the last couple things is we just need a few more points. So I'm going to pick where my asymptote at 2. So I'm going to plug in 3 and see what happens. So I've got 3 plus 6 divided by 3 minus 2 over 3 plus 3. So I plugged 3 in for all of my x values. That ends up being 9. 3 minus 2 is 1. Okay, 3 plus 3 is 6. That ends up being 9, 6, which is 1.5. So I get a second point, 3, 1.5. So I can go 3, 1.5. I can then let the asymptotes kind of guide my direction. Since this point is on the asymptote, we need to find one more. So, okay, if my asymptote's at negative 3, maybe I plug in negative 4 and see what happens. So if I plug in negative 4 for x, I get negative 4 plus 6 over negative 4 minus 2 times negative 4 plus 3. Negative 4 plus 6 is 2. Negative 4 minus 6 is negative 6. And negative 1 plus 4 is negative 1. So I get 2 over 6, which is 1/3 or 0.33. So over here at negative 4, it's just barely up. And all that tells me is that it's going to be above. It's going to kind of come in. Okay, it's going to come. It's going to hit, and then it's going to head towards the asymptote. And so here's a sketch, maybe not perfect, but a sketch of the function. So now we get to the simplify. Okay, the first step in most of these problems is going to be to factor. The first thing I'm going to do here is factor the numerator and the denominator. Factors of 16 that sum to give me 8. Well, that is x plus 4 and x plus 4. Factors of 24 that subtract to give us 2. Well, this time it is 6 and 4. And since it's a negative 2, the bigger of these two numbers has to be negative. So negative 6, positive 4. The second thing we do after we factor is find the restrictions. So the restrictions, again, come from the denominator. So the x minus 6 says that x cannot be 6, and the plus 4 says that x cannot be negative 4. And then the third thing we do is write our answer and see what cancels. So if we look, we have this x plus 4 in common. So we can get rid of the x plus 4's, and then we can rewrite what's left. And if you get rid of the x plus 4's, we're left with an x plus 4 in the numerator and an x minus 6 in the denominator. And we are done with 15. Okay, so now we will look at 16. Same thing, we're going to start by factoring. Okay, z plus 7 this time is on the bottom. Difference of two squares, so we're going to take z plus z minus, and square root of 49 is 7. We're then going to state the restrictions. So the only thing in the denominator is the plus 7, so z cannot be negative 7. And then the last phase is to see what cancels. So this time the z plus 7s will cancel. And what's left is the z minus 7. So my answer is z minus 7, where z cannot equal negative 7. Okay, 17, same thing, but we're looking at multiplication. First step would be to factor, but since this first one's in factored form, we can go ahead and jump straight to the restrictions. So again, looking at just the denominators, this plus 2 says that x cannot be negative 2. The negative 2 says x cannot be 2. The minus 3 says that x cannot be 3. And the plus 1 says that x cannot be negative 1. So we're always going to start with our restrictions. We're then going to go through and see what cancels top and bottom. So I have an x plus 2 that can cancel. And I have an x plus 1 that can cancel. It doesn't matter which one you cancel. If you get rid of everything that you can get rid of, that's going to leave you with what's left. So I have left an x minus 6 over x plus 1 divided by x minus 2, x minus 3. And you could take the time and FOIL this out and rewrite it, but I'm okay with you leaving that answer. Okay, 18 we're going to do the same way, but this time we actually have to factor first. So for these first two, they are both difference of two squares. So I get an x plus square root of 4, which is 2, x minus square root of 4, which is 2, so x plus 2, x minus 2. Same on bottom, but the square root of 1 is 1, so x plus 1, x minus 1. I have my times, so I have an x plus 1 in the numerator. This bottom right piece, all I can do is factor out the GCF. They both have an x in common, so I end up with an x plus 2, so we factor. We're then going to say what x cannot be. So the plus 1 says x cannot be negative 1. The negative 1 says x cannot be 1. Anytime there's a x or a y or a z by itself, it cannot be 0. And the plus 2 says that x cannot be negative 2. We're now going to see if anything cancels. So if we kind of skim, I've got an x plus 1 in top and bottom I can get rid of. I've got an x plus 2 on top and bottom I can get rid of. So that leaves me with an x minus 2 in the numerator, and an x times an x minus 1 in the denominator. Okay, division. Division is the same as multiplication, as long as you remember that we flip the fraction. So we're going to start again, since it's already in factored form, with my restrictions. So again, x by itself, there's no plus or minus, so this 2x says that x cannot be 0. The x plus 3 says it cannot be negative 3. X by itself again says it can't be 0, which we already have. And the plus 3 says it cannot be negative 3. We're then going to rewrite. So this is still going to be x plus 2, x minus 10, divided by 2x times x plus 3. But the division we turn into a multiplication. And when we turn the division into a multiplication, we flip the second fraction. So this is now x over x plus 3 and x minus 10. We then go back to our restrictions. If there's anything in the denominator now that was not in the denominator earlier, we add it to our restrictions. Since we've moved the negative 10 to the denominator, x cannot be 10. So we are now done with my restrictions. We're going to look and see, do any of these things cancel? So I've got an x minus 10 in top and bottom. I have an x in top and bottom. And I have an x plus 3 in top and bottom. So if you get rid of all of those things, you're left with an x plus 2 all over, all over 2. Okay, so you can circle that, or if you wanted to, you could write it as x over 2, and 2 divided by 2 would be 1. Okay, so I'll take either one of those answers. Okay, 20, same thing, but this time we actually have to factor. So we'll go ahead and we'll factor. I have an x squared. Factors of 1 that sum to give us 2. Well, that's x plus 1 times x plus 1. I have divided by. The top here, I can factor out a GCF of x. So I have x, and I'm left with 2x minus 1. In the bottom, I have a GCF of 2, so I have a 2 times an x plus 1. I can go ahead and do my restriction. So the plus 1 says that x cannot be negative 1. The 2 out by itself doesn't do anything because it's just a number. This another x plus 1 says that x cannot be negative 1. So I have my restriction for that piece. We're then going to write this as x squared over x plus 1 times x plus 1. We're going to turn it into a multiplication problem. And just like before, we said when we turn it into a multiplication problem, that says that we flip the second fraction. So 2 times x plus 1 is now in the numerator, and x times 2x minus 1 is now in the denominator. Since we added two things to the denominator, we have to add to our restrictions. So now x by itself says that x cannot be 0. And the 2x minus 1 says that x cannot be positive 1, but then we divide by that 2, so it cannot be 1/2. We're now going to look to see what cancels. So I have an x plus 1 I can get rid of. I also have an x that's going to cancel with the x squared and just leave me with 1x. So then when I multiply this all out, I have 2 times x, which is 2x. In the denominator, I have an x plus 1 times a 2x minus 1. Okay, here we're going to find the LCM, or the least common multiple. Okay, for these, we want them in factored form. We must account for each piece. So if I look for 21, first thing that I notice is there's a 9. Okay, so 9 has to be part of my LCM. So my LCM, I have a 9. Okay, I also have an x plus 2. And if I have it in both pieces, then I only have to write it once. So I now have 9 times x plus 2. And then I have a 2x minus 1, so then I'm going to add 2x minus 1 to my LCM. Okay, so 22, we're going to do the same way, but this time we have to factor before we start. X squared minus 1 is a difference of 2 squares. So to factor, I get x plus 1, x minus 1. Factors of 1 that sum to give us 2. Well, 1 times 1, so I've got an x plus 1 and an x plus 1. So to find the LCM, again, you must account for each piece once. So for starters, I have an x plus 1 and an x plus 1. So I'm going to write x plus 1. But if you notice, there's another x plus 1 that hasn't been accounted for yet. So I'm going to add a second x plus 1 to the LCM. And then lastly, there's an x minus 1. Hey, if you would rather and you recognize that x plus 1 times x plus 1 is just x plus 1 squared, you can write it that way. Okay, but I'll take either one of these answers. All right, so now we're getting to the addition and subtraction. Also remembering to state any restrictions. First thing, if we haven't, or if it's not, I should say, is to factor. So the first thing we're going to do here is factor. So this is really negative 3x. Difference of two squares, we have x plus 3, x minus 3, plus 4 over 2 times x minus 3. Okay, so first thing we did was factor. Second thing we do is identify what the LCM is. So the least common multiple, and when we do the least common multiple, we only care about the denominator. So first thing I notice is there's a 2. Okay, there's also an x minus 3 and an x plus 3. With the LCM, we go ahead and identify our restrictions. So this says that x cannot be 3 or negative 3. The 2 out in front is just a number. Since it doesn't have an x, it does not affect my restrictions. Okay, we're then going to take each fraction, and we've got to multiply by what's missing. So if you look, the first fraction has an x plus 3 and x minus 3, but it's missing a 2, so we're going to fancy 1 times 2. The second one has 2 and x minus 3, so we've got a fancy 1 by x plus 3 over x plus 3. This now allows us to write this as one big fraction. So my denominator is now 2 times x plus 3 times x minus 3. In the top, I have 2 times negative 3x, which is negative 6x. 4 times x is positive 4x. And 4 times 3 is positive 12. Okay, if I combine this, negative 6 plus 4 is negative 2x plus 12. My denominator is still 2 times x plus 3 times x minus 3. And if the numerator doesn't cancel or doesn't factor, then we're done here. But the last thing is to see if we can factor anything. If you notice, there's a 2 in common, and since the lead term is negative, I'm going to factor out a negative 2, which makes this a positive x minus 6, okay, divided by 2 times x plus 3 times x minus 3. Okay, when you factor, if you can then cancel, then you're going to. So if you notice, these 2's can now cancel. So my final answer is going to be negative x minus 6, or you could distribute that negative through. Okay, divided by x plus 3, x minus 3. Okay, 24 is already factored for us, so we can go straight to the LCM. LCM, again, of the denominators says we have an x plus 1, and we have an x minus 1. With the LCM, we can go ahead and state the restriction. So the plus 1 says x cannot be negative 1. Negative 1 says that x cannot be 1. So there's steps 1, 2, and 3. We're then going to take the problem. So I have a 3 over x plus 1 and an x over x minus 1. And we're going to fancy 1 by what's missing. So with the first piece, there is an x plus 1. So I'm going to multiply by x minus 1 over x minus 1. And the second piece has the x minus 1, so we're going to multiply by x plus 1 over x plus 1. This now allows you to write it as one fraction with the denominator of x minus 1, x plus 1. And with that, I'm going to multiply or distribute the top. So the left piece, I've got 3 times x, which is 3x. 3 times negative 1 is negative 3. On the other side, I have x times x, which is x squared. X times 1, which is a positive 1x. I'm going to combine like terms here in the numerator, so I have an x squared. I have an x plus 3x, which is a 4x, and a negative 3. Okay, all divided by x minus 1, x plus 1. At this point, you're going to see if this factors. So are there factors of 3 that subtract to give us 4? And since the only factors of 3 are 3 times 1 and they don't subtract to give us 4, we are done. However, there may be times where you factor the numerator and can keep going and can cancel. But for this one, we're done. Again, to go back to my restrictions, we would add where x cannot equal negative 1 or 1. Okay, 25 was more challenging than I wanted it to be when I originally selected it. So I'm going to come do it last, but 25 is going to be a bonus question and I want to walk you through it, but I'll come back to that one. Okay, 26, start with the LCM. This time it's just a subtraction, but the process is the same. So least common multiple, we've got an x plus 3 here and an x minus 1. Still going to state my restrictions. This says that x cannot be negative 3, nor can it be positive 1. So I have an x over x plus 3 minus 3 over x minus 1, and we're going to multiply fancy 1 by what's missing. So this left piece, has the x plus 3, but since it's missing the x minus 1, I'm going to multiply top and bottom by x minus 1. Over here on the right, it has the x minus 1, but it's missing the x plus 3. So I'm going to multiply top and bottom by x plus 3. This then gives me a common denominator. And we said the denominator was x minus 1 over x plus 3. And I'm going to distribute. So I have x times x, which is x to the second. X times negative 1, which is negative x. I'm then going to distribute the negative 3 to the 3. Negative 3 times x is negative 3x. And negative 3 times 3, which is negative 9. Combine like terms, I get x squared. Negative x minus 3x is negative 4x minus 9 divided by x minus 1, x plus 3. Again, you're asking yourself now, are there factors of 9 that subtract to give us 4? Well, we've got 1 times 9, 3 times 3, and neither one of these will subtract to give us 4. So if it doesn't factor, you are done. Again, restrictions, x cannot equal negative 3 or 1. And 27. 27 was one of our complex fraction problems. Okay, complex fractions, we said we are still going to find the LCM, but of the baby denominators. So if you look, we've got 4 small fractions that create this one big fraction. So when I say the LCM of the baby denominators, what I mean are all these denominators. And if I look for the LCM of these baby denominators, I have an x and I have a y. When it comes to my restriction, since there's no plus or minus, that just means that x can't be 0, nor can y be 0. In the process here, if I go ahead and rewrite my problem, I'll have 2 over x plus 3 over y divided by negative 5 over x plus 7 over y, as we multiply each piece by this LCM. So I'm going to multiply the first piece by xy, the second piece by xy, third piece by xy, and the fourth piece by xy. And then we're going to see what happens. So if you notice, the first piece, the x's cancel. Okay, the second piece, the y's cancel. The third piece, again, the x's cancel. And the last piece, the y's cancel. So the final phase is just to rewrite what we have left. So if you look at the first piece, we have a 2 and a y. So I have 2y. The next piece, I have 3 times x, so I have plus 3x. Negative 5 times y is negative 5y. Plus 7 times x, which is just 7x. And this is going to be my final answer. All right, so now we're going to get to the solve. I check each solution, give the restrictions. The restrictions, as long as you do your algebra correctly, should take care of the check, as long as you don't make any mistakes. Okay, so for this first one, I'm going to start with restrictions. You should factor if you need to, but since it's already in factored form, we're okay. Again, denominator, I have an x minus 1. That tells me that x cannot be 1. And I have a 3x plus 2. So the plus 2 says cannot be negative 2, but since there's a 3 in front, we're just going to divide by 3. Okay, 28 is one I wanted to remind you. You can do the process. However, if you ever end up with a fraction equal to a fraction, you can always cross multiply. So I'm going to cross multiply here, and I'm going to take 3 times 3x plus 2. Okay, on the other side, you're going to take 4 times the x minus 1. Okay, so equals 4 times x minus 1. And once you get cross multiply, we're just going to distribute and solve. So I've got 3 times 3x, which is 9x. 3 times 2, which is 6. On the other side, 4 times 4x and 4 times negative 1. So 4x minus 4. I'm going to subtract 4x from both sides, which gives me 5x plus 6 equal to negative 4. I can subtract 6 from both sides. So 5x equals negative 10. Okay, the last phase, if I divide by 5, that gives me x is equal to negative 2. As long as you've done all your algebra right, and your answer is not one of your restrictions, then usually that is pretty good. Okay, if you wanted to check, I'll show you one of these real quick. But you could plug back in and see if it works. So I have 3 over negative 2 minus 1. And we're going to say, okay, does that equal 4 over 3 times negative 2 plus 2? Well, negative 2 minus 1 is negative 3. Negative 2 times 3 is negative 6. So this is negative 1. 4, negative 4 plus 2 is negative 4. And negative 1 equals negative 1. So that confirms that it works. Okay, 29. Again, first step would be to factor, but I'm giving you this one also in factored form. So we're going to start by finding the LCM. So if you look at the denominators, I have an x, and I have an x plus 3. Okay, the LCM also helps us get our restrictions. So that says that x cannot be 0. The x plus 3 says it cannot be negative 3. Okay, this time it's a little bit different. So I'm going to take my 2 over x plus 3 minus 1 over x equals negative 6 over x times x plus 3. And this time you're going to multiply everything by the LCM, which is 6 times x plus 3. Okay, so if you look at the first piece, if I multiply the first piece by the LCM, the x plus 3's cancel. If the x plus 3's cancel, then I am left with 2 times x. Now if you do the second piece, this time the x's would cancel. So I would be left with a negative 1 times an x plus 3, because this time the x plus 3 would stay. If you look at the last piece, it's got x and x minus 3, which means the whole thing would cancel. So I would just be left with the negative 6. So once you multiply everything by the LCM, you cancel what can cancel. We're now going to solve. So 2 times x is 2x. If I distribute this negative through, I get negative x minus 3 equals negative 6. 2x minus x is x. So x minus 3 equals negative 6. If I add 3 to both sides, I get x is equal to negative 3. And however, we said earlier that x could not equal 0, nor could equal negative 3. And right here, we're saying that x equals negative 3. So if my answer is ever equal to my solution, we said that this was called an extraneous solution. And if your only answer is ever an extraneous solution, then your final answer is that there is no solution. Okay, 30. So 30, we actually have to factor before we start. So I'm just going to take this piece right here and underneath write it in factor form. So factors of 12 that subtract to give us 1, that's 4 and 3. And since it's a negative 1, we want the bigger number to be negative. And we're then going to use factored form to find the LCM of denominators. So we have an x plus 3 and an x minus 4. Okay, denominators will tell us what x cannot be. So the x plus 3 says that x cannot be negative 3. And the minus 4 says that x cannot be 4. So we have 2 over x plus 3 plus 3 over x minus 4 equals 2x minus 2 divided by x minus 4x plus 3. We said for solving, once we get the LCM, we're going to multiply everything by the LCM. So we're going to multiply everything by x minus 4x plus 3. Maybe this time I'll actually write it on there. So if you're struggling with seeing what I'm doing, I'll do it this way this time. So I'll come and say x plus 3, x minus 4. And here I'll put x plus 3, x minus 4, and here I'll put x plus 3, x minus 4. Okay, so when we look at the first piece, the x plus 3s are going to cancel. Okay, the second piece, the x minus 4s are going to cancel. And the third piece, they both cancel. So then we can rewrite what's left. We rewrite what's left. The first one has 2 times an x minus 4. Second piece has a 3 times an x plus 3. And the third piece is just left with the 2x minus 2. And now we can solve. So I have 2 times x, 2x. 2 times negative 4 is negative 8. 3 times x is 3x. 3 times 3 is 9. Equal to 2x minus 2. 2x plus 3x is 5x. Negative 8 plus 9 is positive 1. So I'm going to subtract 2x from both sides. At the same time, I'm going to go ahead and subtract 1. So if I come up here, that gives me 3x is equal to negative 3. And when I divide by 3, x is equal to negative 1. This time, if you notice, the answer is not a restriction, so we can go ahead and leave it alone. Okay, so that concludes majority of the review. I'm going to go back and do 25, which I haven't worked it yet, but I think it's going to be a little bit more lengthy than I wanted it to be. So this will be a bonus type problem on the test because you'll see the LCM, I think, has 3 pieces. Okay, so first thing I'm going to do is factor. So this first piece, factors of 3 that subtract to give me 2. I have a plus 3 and a minus 1. Here, difference of 2 squares, so we get x plus 2, x minus 2. So when it comes to the LCM, we have an x plus 3. This is that. We have an x minus 3, or sorry, x minus 1. We have an x plus 2, and we have an x minus 2. LCM helps us find the restrictions, so x cannot be negative 3, 1, negative 2, or 2. Okay, so when we look, we want to get a common denominator. So I'm going to, now, again, because it's a bonus question, I'm going to just say this. This piece needs that. Okay, and this piece is missing that. Okay, so to make this a little bit easier on us, I'm going to go ahead and write my denominator, which has got all the pieces. It's going to have an x plus 3, it's going to have an x minus 1, it's going to have an x plus 2, and it's going to have an x minus 2. Okay, I'm going to have the x squared minus 1. And to fancy one, what this is missing is this right here. So I'm going to multiply by x squared minus 4. I have my subtraction. I then have an x plus 1. And this piece on the right is missing what's over on the left, so I have to multiply by an x squared plus 2x minus 3. Okay, from here we have to distribute or FOIL or multiply out. First thing I'm going to do is write this as a plus negative x minus 1. And then I'm going to do some multiplying. So x squared times x squared is x to the 4th. X squared times negative 4 is negative 4x squared. Negative 1 times x squared is negative x squared. And negative 1 times negative 4 is a positive 4. On the other side, I have negative x times x squared, which is a negative x squared. Or sorry, negative x to the 3rd, excuse me. And negative x times 2x, which is a negative 2x squared. Negative x times negative 3 is a positive 3x. Then move on to the negative 1. Negative 1 times x squared is a negative x squared. Negative 1 times 2x is a negative 2x. And negative 1 times negative 3 is a positive 3. And all of that would be divided by x plus 3, x minus 1, x plus 2, x minus 1. And when we look, we'll see if we can combine any like terms. So I've got an x to the 4th. And then I have a negative x to the 3rd. and then having negative 4x squared minus x squared, which is negative 5x squared, minus 2x squared, which would put me at negative 7x squared, minus x squared, which would put me at negative 8x squared. I then, excuse me, have a 3x minus 2x, which would be a positive x. And then lastly, 7 plus 3, or 4 plus 3, which would be 7. And since that does not factor cleanly, we would just leave it all over x plus 3 times x minus 1 times x plus 2 over x minus 2. But I think I typoed, and that would be my final answer because I do not think it was supposed to be this complicated. All right. So that concludes the review. Good luck with your studying.